In today's lesson, we're going to be looking at derivatives of exponentials. Before we get into talking about derivatives of exponentials, we want to talk about what the number e is. It's an irrational number, and this is the number to approximately 6 decimal places. We want to talk about how this number came about, how it's related to this limit. There became a need to find the derivative of an exponential function. So let's define an exponential function as a to the x. By definition, the derivative f prime at x is the limit as h goes to 0 of a to the x plus h minus a to the x over h. Well, doing a little bit of algebra here, we can see we can factor out that a to the x, and we'll be left with a to the h minus 1 over h. This x has nothing to do with the limit, so we can take that out, in which case we get a to the x times the limit as h goes to 0 of a to the h minus 1 over h. Now if you take a look at this limit here, this is exactly equal to, given that our function f at x is a to the x, by definition, this would be equal to f prime at 0. Therefore, this will equal f prime at 0 times a to the x. Let's put this together and see. Therefore, we have f prime at x is equal to f prime at 0 times a to the x for any exponential a to the x. So what that means is the derivative of any exponential function is just itself times some multiple of that. Now that we have this result here, where the derivative of any exponential of base a is just proportional to itself, what we want to do here is take a look at what happens if you let a be 2. Well, if I let a be 2 here, if you examine the table that we've drawn here, we can see that the limit as h goes to 0, so as h tends very, very close to 0, we can see that the limit is 0.6923. Therefore, for a base of 2, we know that f prime at x is going to equal approximately 0.6932 times 2 to the x. And likewise, if I let a be 3 here, and we examine a base of 3, we can see here that f prime at x is going to equal 1.103 to the x. So therefore, the derivative of an exponential of base 2 is approximately equal to this, and the derivative of an exponential having a base of 3 is approximately equal to this. Between 1.10 and 0.6932 lies the number 1. So what we're going to do is we're going to let e be such that number, such that the limit as h goes to 0 of e to the h minus 1 over h is equal to that 1. So in summary, e is a number that is between 2 and 3, and is defined in such a way that its limit as h goes to 0 of e to the h minus 1 over h is equal to 1. Let's take a look at using this result to find the derivative of e to the x. We want to be able to show that the derivative of e to the x is itself. By definition, f prime at x is the limit as h goes to 0 of e to the x plus h minus e to the x over h. Doing a little bit of algebra, we get, recall now that I have factored out the e to the x, and notice that this is independent of my limit as h goes to 0, so I can take that e to the x out of the equation, in which case we end up getting. Now recall here, we got into this situation previously, but we did not have a base of e chosen. We had a generic base of a. But because we've chosen the base of e, which is a number between 2 and 3, such that its limit as h goes to 0 is 1, we can now conclude that f prime at x is e to the x. So therefore the derivative of e to the x is itself. Let's take a look at applying this derivative to various problems. In our first example here, we want to take the derivative of y equals e to the negative 3x times the cos of 2x. So taking our dy dx here, this is going to be the product rule. So you're going to have the first function times the derivative of the second. Well, that's going to be negative sine of 2x. And now the chain rule comes into play. We have to go ahead and take the derivative of the inside, in which case that's going to be 2. plus your second function, in this case cos of 2x, times the derivative of e to the negative x will be itself. But again, that was not just an x, so using the chain rule, the derivative of negative 3x is negative 3. Cleaning this up, we get negative 2 e to the negative 3x times sine of 2x minus 3 e to the negative 3x cos of 2x. We can go ahead and factor out negative e to the negative 3x, in which case we get 2 sine of 2x plus 3 cos of 2x. This is a good form to leave your first derivative into. If we want to extend this further, we wanted to find values where the first derivative is 0, we could set this equal to 0. We already have it set as a product of two expressions, and we could go ahead and solve for x for this. All right, let's look at another. For the next example here, we want to go ahead and take our derivative. So let's go ahead and say dy dx. Now the derivative of tan is going to be secant squared of our input. But again, that was not just an x here. That's an e to the x. I have to take the derivative of the inside, in which case it's just itself for an exponential with base e. So this becomes dy dx is going to be e to the x secant squared of e to the x. All right, let's try another. Here, y prime is going to be equal to, well, the derivative of e to the x is itself. So we're going to go ahead and write that back down. Now you have to take the derivative of the top. Again, the top was just not an x, it was an x cos of x. So now the product rule comes into play. It's going to be first times the derivative of cos x is negative sine of x plus your second, and then derivative of the first is just 1. So simplifying this, this becomes e to the x cos x times cos of x minus x sine of x. Let's try another. So for this question here, they want you to find at what point or points on this curve is the tangent line parallel. Well, the slope of this tangent line is going to be negative a over b if you're in standard form, which we are, in which case here this is going to be negative 3 over negative 1 is 3. So therefore, the slope that we want for our tangent equation has to have a slope of 3. So we're going to go ahead and take our dy dx here, in which case we get derivative of 1 is 0, derivative of 2 e to the x is just going to be 2 e to the x, and then derivative of negative 3x is minus 3. We're going to go ahead and set that equal to 3. Solving for x here, we get 2 e to the x is going to equal 6. E to the x is going to equal 3. Take the ln of both sides of our equation, in which case here we get x equals the ln of 3. Subbing this in to find our corresponding y value, we get y equals 1 plus 2e to the ln of 3 minus 3 ln 3, in which case here we get 1 plus 2 times 3 minus 3 ln 3, and we get 1 equals 7 minus 3 ln of 3. So the point on the curve, y equals 1 plus 2 e to the x minus 3x, that is parallel to the line given in the above equation, is ln 3, 7 minus 3 ln 3. So for the following example here, they want us to find the 1,000th derivative of the following function. So obviously in this situation here, we have to establish some sort of a pattern. So let's go ahead and try that here. We got our first function is x e to the negative x. Let's go ahead and find f prime at x. Well, f prime at x is going to be first times the derivative of the second plus the second times the derivative of the first. So simplifying this, we get negative x e to the negative x plus e to the negative x. Let's go ahead and take our second derivative. Well, the second derivative is going to be the first times the derivative of the second is e to the negative x to the negative 1 plus the second, and then the derivative of the first is negative 1 plus e to the negative x times minus 1. So simplifying here, f double prime comes out to be x e to the negative x minus, if you notice here, we end up getting two of these. 1, 2, and both of them are negative. So this is going to be negative 2e to the negative x. Let's go ahead and take the third derivative. Well, the third derivative here is going to be first times the derivative of the second plus second times the derivative of the first is 1. Now we want to take the derivative of this expression. Well, the derivative of this expression is going to be itself times the derivative of the negative x, which is negative 1. So therefore, f triple prime at x becomes negative x e to the negative x. And you'll notice here, minus 2 and the minus 1 become positive 2. So this becomes plus 3e to the negative x. A couple more of these, I think we'll be able to establish the pattern. Let's go ahead and take our fourth derivative at x. Well, the fourth derivative is going to be the first times the derivative of the second plus the second times derivative of the first plus taking the derivative of this term here, it's going to be itself times the derivative of that negative x. Putting this together and simplifying, we get x e to the negative x minus 4 this time, e to the negative x. So let's take a look here. We've got our first derivative gives us the following. Our second derivative gives us the following. Our third derivative, we've got here alternating, notice the alternating negative, positive, negative. And lastly, our fourth derivative here is back to positive. So if we were to establish a pattern here, we'll notice at 1 and 3, it is negative. At the even powers, it is positive. And first derivative, we have a 1 e to the negative x. Second derivative, we have a 2 e to the negative x. Third derivative, a 3 e to the negative x. And lastly, the fourth derivative, a 4 e to the negative x. Also notice that on these terms, a power of 1 makes this positive, a power of 2 makes this negative. So if we had to put this all together and express this in general terms, what would the nth derivative look like? Well, the nth derivative would be, you're going to have an x e to the negative x in there, and you're definitely going to have a n e to the negative x in there. The question becomes is how do you adjust the minus signs? Well, when n is even, notice that this becomes a minus sign. So if I put in here plus a negative 1 and I raise that to the power of n, this would be no good. Because if n is even, like 4 for instance, I actually want a negative value here. So therefore, if I were to add 1 to that, that'll always ensure that this will be minus when n is even. Likewise, I want the coefficient in front to alternate between positive and negative. Well, if n is 4, it's going to go ahead and make this positive, which we have positive. Notice if I let n be 3, if we want to match our equation for 3, if I let n be 3 here, this will be negative, which we have a negative, and this will be 3 plus 1 will be power 4, making this positive, and you still have your n value of 3 here. So the general equation here is the nth derivative of our function is going to be negative 1 to the power of n x e to the negative x plus negative 1 to the power of n plus 1 times n e to the negative x. So therefore, if I want the 1000th derivative, it becomes easy task now. Obviously, the 1000th derivative at x is going to be 1000 is an even number, so that'll make this positive. So this will be x e to the negative x, and 1000 plus 1 will make this negative, and this will be 1000 e to the negative x. And now we have a general equation for the nth derivative of our function. Okay, that concludes today's lesson. Thank you.